Good morning, I'm Technical Sergeant McCusker. This is Block 2, this is Section 3 Alpha. We are going to identify the relationships of basic facts and state general principles about the functions of the high-frequency HF transceiver. The minimum score for your test is 73% for the block test. However, y'all are going to do a lot better than that. So there are many different HF radios in our career field, and typically I'll read this part like I'm in that scene from Full Metal Jacket in the beginning, where he's like, "This is my rifle." So each may be slightly different, but the basics are the same. Understanding the following theory of block diagrams will give you a better understanding of how these HF radios function. Airman Mate, did I get your name right there? Did I mess up? McChesky, sorry, excuse me, Airman McChesky. How do you think this information will help you in your career? Not just with an HF radio. Let me ask you that.
It's gonna help you, like, when you look at any radio. I'm pretty sure they're probably all of the similar, like, basic design.
That's really good. What are some things, Airman O'Brien, that you think are important when you are going through circuits and diagrams? Like, we may not be maintainers, for example, anymore, like we used to be when I came in, but why would being able to understand component level help maybe with troubleshooting? What do you think about that?
Just so you understand more where if there's something wrong with the radio, at what point in like the system of the radio that the problem is occurring.
Yeah, absolutely. You know what else it'll help with? When we do this thing that you guys may have heard this term called swaptronics. When you go to send these radios back to Harris Corp or wherever they came from, they're going to be able to quickly turn around that radio much faster than if you had given them no information and told them, hey, this radio's broke. Good luck. Awesome. So here's some things we're going to talk about in Section 3 Alpha. We got the assemblies, the hub battery, which you all are very familiar with that already, the transmit signal flow, which clear voice, data encryption, and I went over what clear is yesterday. Does anybody remember? Not like going clear as in Scientology.
I'm not sure we understand, like, what you're asking here.
What is clear voice? What does that mean? If something is clear, for example, my coffee cup. My coffee cup is clear. Here, let me show you guys. See if you can see this.
Is the clear
Damn,
voice
you
like
can see me now.
non-encrypted?
Y'all see this? This
text?
clear coffee cup here. Yes, clear coffee cup.
Oh, that's a clear coffee cup?
That's clear. Can you see through it? It means it's clear. That means you can. That means you can see through it. Did you guys see that when I turned the video on for a second?
No, we did not.
No, we didn't see anything.
Oh, okay. That was weird. Oh, it should have showed up for y'all when I turned it on. Okay. Well, my coffee cup is clear. That was the point I was trying to get across. If it's clear, it means you can see through it. There's nothing in it. As in, there's no encryption. There's no data being transferred, but there's no encryption on there. So that's another term for no encryption. It's clear. Clear text, clear data, clear audio. You may hear this term in your careers, and I want you guys to understand what it is now, because that will help you later.
So basically, it's a non-encrypted voice?
Yeah, it's non-encrypted. That's all it means.
So clear voice is the same as like
plain text. Clear voice is the same as plain text is clear voice. Yes. And that's something we're going to get further into today. So understanding those terms and those things we talked about yesterday is really going to help you all out today. If you guys understood what I was talking about yesterday, for sure. Yeah, I turned my video on for a second there, but I guess you guys couldn't see me. It's probably a good thing I haven't shaved in like a week. Y'all don't want to see that. All right, let's keep going here. So for theory of operations, we got the clarification for assemblies, subassemblies. A2 is the designator for entire assembly. This assembly has many submodules. For example, A2A1, A2A4, and A2A5 as examples. These are submodules or subassemblies. And an assembly, one of the easiest ways to explain this to you guys is to literally go forward to the actual circuit and diagram we're going to be working on here today. Now let me enhance here for you. Now that I have this blown up, Yeah. Now that I have this blown up, go ahead.
So they actually yesterday, the instructor there, he gave us 2 sheets that have the whole diagram like on a piece of paper.
Y'all want to bust those out real quick? Because you are going to need those. And maybe some colored pencils. Now, I will tell you, those sheets he gave you, those are also available digitally inside of that intermediate maintenance manual in the TO. And that's probably something he didn't tell you because we typically don't tell you all that because y'all would rather look at the paper copy, which is fine because you get a paper copy for your test. But if y'all want to take out the paper copy and you want to write notes on it as I go through this stuff later, that's fine because there's a lot to get through today. Typically when I teach this part in person in class, it takes like 2 hours to 3 hours, but we're going to condense that a little bit. Now, the point we were getting at is this is A2, correct? What I highlighted here, y'all see this? It says A2, lower chassis or chassis assembly. Verbal response is good, typing is good.
Yes, sir. Here, we see it.
Perfect. When we talk about A2, we talk about all of the things that A2 does. We talk about this audio cleanup, this modulation, digital modulation that happens in here. We talk about turning analog to digital and then back again. We talk about all of these things when we talk about A2. So think of A2 as you taking a paintbrush and a canvas and you're just starting that painting and you want to maybe get your primer on there or you want to get your base coat, or for example, you're painting a model or a miniature like I like to do in my free time. You're spraying it with your base coat first. You want to kind of get those broad strokes on there and get a whole thing covered before you start getting your finer details on there. When we talk about an assembly, we talk about that broad stroke. We talk about having the entire thing covered, the whole page covered right here. All of these things that are happening in A2 at once. We'll talk about it, but we'll talk about it briefly. Now, if I want to know the specifics, as I like to call them, or the specifics, we're going to talk about a subassembly. And y'all passed kindergarten, correct? I mean, you wouldn't be here if you didn't. Yes?
Yes, sir.
Yes.
Awesome. That one took a minute. This is interactive, guys. You're allowed to talk. It's okay. A2, A4 is this whole cutout line here. You see these little cutout lines like we're doing in kindergarten? You gotta cut along these dotted lines. Some people get a little crazy and start cutting like this every once in a while. I don't know. I did that. Maybe y'all didn't. You cut along these lines, and everything that happens in here is now specific. We specifically want to know, if I ask you what is happening in A2, A4 at the ALC, I want to know what's happening in A2, A4 at the ALC. If I say what happens in general in the A2 assembly, I just want to know what happens overall here. I want a broad strokes overview. And that's what we get at when we're talking about the difference between an assembly and a subassembly, or a module and a submodule. And that's what you guys are going to learn about this morning first. I just kind of wanted to clarify those two differences. Did that help y'all?
Yes, sir.
Perfect. Because I know sitting here and reading the stuff in your dorms, it's very difficult to try and understand all this.
For this class, do we need to know like what all the subs do, and
Do you think you need to memorize this stuff when I'm about to give you a table in the intermediate maintenance manual, or do you think that if you had your intermediate maintenance manual open right now and had a general idea of where this stuff was, that it'd be a lot easier?
Yes, sir.
Yes. So go ahead and open up you guys' intermediate maintenance manuals to table 3-1 as we go through this next section here. And I'm literally just going to kind of read through these next couple slides because they are verbatim from your TO. Everybody goes to table 3-1 in the intermediate maintenance manual.
Do you know what page?
Just type in Control F and hit 3-1. Table 3-1. I don't know the exact page reference for you. One of the things I like to talk about first is the A1 because we need to go in order when we're going through circuit flow. It doesn't make sense if you don't. When we go to A1, what do you guys think this is here? Because I like to call it the turtle shell. Y'all remember working on the radio yesterday?
Yes, sir.
Perfect. I like to call this thing here the turtle shell for two reasons. One, the radio worked on screen, is it not?
What'd you say?
The radio you worked on yesterday, it's green. Yes?
Yeah, it was great.
It was green. Turtle shells are green last time I checked?
Yes, sir.
Perfect. What do turtle shells do for a turtle?
Protects the turtle and everything that's inside of it.
What do you think the A1 chassis does for the radio?
Protects it with its
Protects it.
life.
Protects it. Yep, exactly. It protects it. That's his job. It'll protect it from elements, dirt, sand. Maybe not sand so much. Sand gets into everything. Y'all figure that out if you ever deploy. I don't know how, but it does. A1 chassis. A1 protects the A2 lower chassis assembly and A3 upper chassis assembly. So it's just like the turtle shell there. It protects the guts of the radio. It receives direct current DC power from the A4 rear panel assembly and distributes DC power to the other RT assemblies. Y'all know RT just stands for receiver transmitter.
Yes, sir.
Cool. Provides a mounting structure for the front panel interface, the connectors in the A5 KDU. If you guys did not know this, you can actually take this right here, this little slide it to the left, and then it will pop off, and you can remove this KDU or MMI, and you can remote it up to about 6 feet away. With A2, it processes the voice and data signals. It supervises control functions for the entire radio, also contains the encryption, the crypto assembly. And remember the stuff I'm going over right now, I'm not going over those specifics I was asking y'all about. I'm going over just broad strokes. A3 contains the analog RF sections of the radio. It has a receiver, exciter filters, power amp, and tuning circuits, and an analog output of 240 kilohertz. It's the first IF. So A3 is our analog RF sections of the radio. A4 is our rear panel assembly, and I kind of briefly talked about this yesterday when I mentioned the hub battery, and when you guys see this flipped around in a second here, you're going to see that. It contains the radio power supply assembly, provides the interface, the connector to the batteries, the hub, and the hub does what? What is the job of the hub?
Protects the memory of the radio when the power is off. For, like, the
Perfect,
circuit.
perfect. What is the memory it's protecting?
Is it protecting like your presets and stuff like that you have
Yep,
set?
your presets. Perfect. Will it protect those things if I zeroize the radio?
No, sir.
No, it will not. Very good. That's a great thing to know. Remember that for your careers. Anytime somebody says they zeroize something, you might as well bring crypto and everything else you need with you, because you're going to start from scratch. Continuing on the A4 rear panel assembly, we got the hub, like you guys said. It protects the memory, those system presets. How many system presets do we have?
Don't we have like 5?
Negative. You have up to 75 system presets. How many channels do you have?
75?
Negative. You have 200 channels. Where is that information available?
TO.
Which TO?
Operations.
Perfect. Operations type things are in the operations manual, such as programming, how to briefly fix the radio, things like that. Other more in-depth maintenance options and C's and D's are located where?
Intermediate. Maybe?
Intermediate maintenance manual. Very good. Next, we talk
So
about the
you're
J9. Yep, there you go. You'll get it. Next, we talk about the J9 accessories. That's the J9 accessory connector. Just like KP, we don't do what?
Don't touch.
Don't touch it. You drop a glass in KP, you don't touch it. So J10 and J11, that's next. That's the battery connectors you all looked at yesterday. Here they are. That's what the hub battery actually looks like. That's the nomenclature for the hub battery if you have to order one from the company. Here's some covers. It's got a little gasket around it. All this stuff like pops out when you remove it. This foam tape is probably going to look like it's all molded out and gross, because I've never not run into one that doesn't look like that when you remove it. I don't know why. Maybe these things are just old. It's entirely possible. And then we go to A5. A5 contains the keypad and the LCD that makes up the radio's man-machine interface, MMI, which is another name for the A5 KDU right here. Now this is the section I told you all to go ahead and open your TOs up, so I'll give you a quick second to do that. Go to paragraph 3.3.1.1, and I need you to be following along as I go through and explain some things to you about the actual circuits and diagrams of the radio here. So I'll give you guys a second. Does anybody want to grab their sheets real quick or not have their sheet right in front of them?
What paragraph is it again?
3.3.1.1. The video chat keeps connecting and disconnecting for you, Evan Smith? Okay.
I'm finally. I don't know what was going on, but I'm back.
Okay, I just want to make sure you're good.
So are you gonna zoom in on the?
Oh, we're going to go through it. I was giving you guys a second to open everything up.
No, yeah, I know. I was just wondering if you're gonna zoom in when we do.
Yep, just like this. So the next slide I actually go to is going to be these different sections as we go through here. So no need for me to zoom in. Now, the first question I always ask when we come through here is what format is audio in? Is it digital or analog?
Analog.
Digital.
Oh, I got two different answers. Which one's the correct one?
Digital.
Why would you say digital? Do you talk in digital? Do you talk like a robot?
Remembering it wrong because I read it all yesterday.
That's okay. So do you talk like a robot? That's my question to you.
No.
No. So you're not speaking in digital format, correct? We don't talk in ones and zeros. I don't wake up in the morning and go 00101000101, sir.
No, maybe I was thinking of it backwards because like I read it all through and read the receive last and was
Understandable, understandable. And you guys are students, and this is why we're in here. Is it not? We're all in here to learn. So audio comes in as analog format. That's the point I'm trying to get across here. If it came in as digital, we wouldn't even need that AIC right there, which is one of the things we're going to talk about, which takes it from that analog format and then digitizes it. Now, if we were talking about data down here, J3, what would that come in as?
Digital.
Digital. Yeah, data's already digital, so we don't need all this fancy stuff we have up here, and we'll get to that later. Now we come in through J1 audio because you all hooked up your J1 audio handsets yesterday. You hooked up your handset to that plug. You guys see this? It's our little handset there. You hooked it up to the J1 audio. You started speaking through the radio. You said, headquarters, this is Raptor, how me, over, something like that. Yes? You gave a call sign. You gave your call sign. You said, this is my call sign. I'm looking for a radio check. How do you understand me? And all of these things happened instantaneously, did they not?
Kind of, yes.
Near instantaneous. I mean, some of you probably forgot the antenna, which happens. You don't have to call each other out if you forgot the antenna. I did it the first time I did the lab. It happens. You're just standing there going, I don't know why it's not working. It's good stuff. So we come in as analog, like I was saying. We go to this ALC here. That's the first thing we go to. It's the the automatic level control, ALC. That's what ALC stands for. And if you're following along in that paragraph 3.3.1.1, it says exactly these things I'm going to tell you. I have these things committed to memory. Not that that's something you need to do. You need to be able to read your TO and understand it. We talk about this ALC. The ALC takes that varying voice level, that level that comes in really high or really low or really squeaky or mousy or whatever you do with your voice, and adjusts it so that the radio can understand it and makes it constant, because we don't want to have things fluctuating as they go through finer tuned circuitry in the radio. It'll cause some problems. It might cause an increase in gain level. It might cause some voltage problems, things like that. And some of these circuits are very sensitive. So the radio needs to adjust those levels and make them constant as they come in, because it needs to process them at a certain level. That is why this thing here exists, this ALC. Next we go to the IC, that's the analog interface chip. And no, I don't mean like Doritos or Lay's chip. I mean a computer chip. It'll take that analog, turn it to digital. Why do you guys think we're going to go from an analog to a digital format? That was a question.
Because it's going through a circuit.
Yeah, it's going through a circuit. Okay. What else? What do you know about digital communications? Are they easier to process through analog methods or through digital methods? Is it easier to manipulate data than it is to manipulate an analog signal?
Yes, sir.
Yeah, absolutely. It's much easier to process and manipulate something and modulate something that's digital versus modulating something that's analog. You have more things you can do with it, more ways they can send it, more ways to process it, things like that. Now, one of the things we go to next is called the VDP. That's the Voice Data Processor. Its entire job is just to sit there and clean up that audio, that high, that low voice, that squeaky, mousy, whatever voice that's coming in. It's going to clean that up and it's going to make it more sound like your original voice. Now, one of the things you guys probably saw yesterday is, did they hook up not the spectrum analyzer, but the CSM or CSA in the back of the room and kind of tap into your audio? Did they listen to your audio when you guys were talking to each other? And it sounded like a robot talking in the room?
No, I don't think they did it with us, sir.
What? Nobody did that? Well, that's one of the things you can do. You can intercept the audio line if they hook it into the front of the CSA or the CSM, and as you guys are talking through there, it doesn't really have one of these VDP things in here, inside of it, because it's not designed for that. So it can't make the voices coming through sound like the original voice. It doesn't have the small circuitry that's inside of the radio. So you guys will sound like you're talking like this, like you're talking into a voice changer. That's what it'll sound like coming through there. Male, female, whatever, it all sounds the same. That's interesting that they didn't do that. I thought they did that for y'all. Next, we go to the PTFPGA, or as I like to call it, the traffic cop, because plain text field programmable gate array is a huge mouthful to remember. What is the entire job of a traffic cop?
Direct traffic.
He directs traffic. What do you guys think happens when you turn the switch to CC? Just looking at this circuit.
Redirects the digital signal.
Perfect. It redirects that digital signal and sends it up here to CC. What about CT? What's it going to do?
Sends it up to the CT part.
Perfect. Sends it up to the CT part. Now, quick question for y'all, and we'll go over this again towards the end here. This A2A5 embedded crypto assembly for CT is separate. Why do you think it's separate? Do you think it's part of the A2A4?
No, because this is A2A5 on top.
Perfect. It's its own subassembly. It's its own little thing. Remember, this is for the type 1 encryption that we do not share with our NATO allies. This is the one that we share with NATO and allies here, and this is the one that's programmed from either remote capabilities or programmed from the front panel of the radio. And we'll come back and talk about that again. Very good. Since we're in plain text mode, we're going to go down here. We're going to follow these little arrows. And we're going to come to the CFPGA next. That's the Control Field Programmable Gate Array. That's not really going to do too much to our signal because we're not processing data right now. So we do not need to go through the modem up there, as you guys see, the modulator demodulator, because that is what modem stands for. We do not need to go through that at all because it's not data. Next, we're going to go to the CDSP. That's the Control Data Signal Processor. And if you're following along in your TO, like I told you all to do, it's going to say the same thing like the CFPGA. It's just going to pass that information along. That's all it's going to do. That's it. We will then go to what's known as the digital modulation portion of the radio, which you guys will hear A to A1 and digital modulation together quite often because of this small circuit right here, this DIF-ASIC, which stands for Digital Intermediate Frequency Application Specific Integrated Circuit. No, you do not need to know that, like memorize that. You do need to know what it's doing, but you do not need to memorize that. It modulates and takes that digital to analog conversion take place. This is before that digital analog conversion takes place, and it's the first IF being created here. It's a 240 kilohertz digitally modulated produced waveform. That's what this does. It's going to give us this 240 kilohertz, but it's not in analog format yet. So we need to pass it on to the digital IF, D/A, digital intermediate frequency, digital to analog converter. That's all this thing's doing. It's a little converter, taking it, turning it back to analog. And there's a reason for that, because when we go to A3, the next section of the radio, it has to be in that analog format, because the A3 section of the radio is what's known as the analog section of the radio. That's where we're going to take this analog format and convert it into RF so we can send it out of our antenna. And we can shoot our signal out across the ionosphere to our other HF partner out there, or our other FM signal to our line of sight plane or other sister service radio we're trying to talk to. Any questions so far?
So the modem would only be used if we had stuff going through the J3 data part?
Yes and no. For right now, yes, we will send data through there, but also you see how it says CT data? If anything is encrypted, and we're going to get into this when I talk about encryption, because after we do the entire transmit path, we come back through and talk about encryption, but that's fine, I can talk about it right now. If we were to go through this CC mode here, this Citadel cover mode, notice that it goes through this, the ciphertext field programmable gate array. That's what is specifically designed for ciphertext and Citadel cover mode. And it's going to send it out and go through this thing, the BIOP, the black input output processor, which is maintains system control status functions for the KDU and for the radio. And it also sends that information to the modem. So if it's encrypted, it has to go through the modem as well, regardless if it's data or audio. So that was a good question.
Okay, yeah, so encrypted will always go to the modem.
Encrypted will always go to the modem.
So if it's unencrypted and it's data, then it will go there too. But if it's
Correct.
audio, then it'll just go through.
Correct. Very good. Very good. So you're getting it. Another thing to note here is this is the first IF being created right here in transmit. And there's a reason I'm saying in transmit, because when we come back through and do the receive side, y'all are going to notice some differences. They're subtle, but you're going to notice them. Any questions so far before we move on to A3? You're asking great questions, by the way. Let me look and see if anybody's typing here. No. Aaron Wright says no. He gets everything. Perfect. Aaron Wright says I'm going to get 100. I was waiting for him to type something, but he didn't contradict that at all.
That's a she.
Oh, my bad. Excuse me. Aaron Wright says she's going to get 100. Next, we go to the 13 dB attenuator. What do you guys know about attenuators? Do you know what they do? Did they teach you in Dolan Hall what they do?
No, sir.
Perfect. The point of an attenuator is to drop the signal level down, and there is a great definition I always like to grab from Google here for y'all about an attenuator, because I think it's important to know what they do, because we will use them often in our career field. Let me get that definition for y'all. Here you go. See if y'all get this. Perfect. Y'all see that? So an attenuator is an electronic device that reduces the power of a signal with impeccably distorting its waveform. While an amplifier provides gain, an attenuator provides loss or gain less than 1. When we use an amplifier, we're using it to raise our gain level, increase that signal strength. That's the whole point of an amplifier. And you guys are going to see those in this circuit we're about to go through. But first we have to drop it down and get it to a level we need it at. We need to drop it down by 13 dB because that allows for the proper input for the second IF input. If it wasn't dropped down, we wouldn't get this exact signal level we're looking for here. And remember, that's what I was telling you guys about things like the ALC, and you've got all these small circuits in here that are going to specifically tune things so that when they get sent to something in here, or like a mixer or header or whatever's happening, it has to be at a specific level. Otherwise, your signal will get distorted and messed up and cause all kinds of problems. Next, we're going to go through a low-pass filter. It says that anything less than 1 megahertz will pass unchanged to the next stage. Now, if I have a signal that's 2 megahertz, is it going to get through?
No, sir.
No. What's it going to do? What's a low-pass filter going to do to a 2 megahertz signal if we had one, hypothetically speaking?
Stop it in its tracks.
It's not going to stop it, actually. What is it going to do? What does it say right here? It says the word unchanged, correct?
Yes, sir.
It's going to take that 2 megahertz filter and it's going to get it down to the level it needs it at. It's going to get it to that 1 megahertz level, or less than 1 megahertz. Make sense? It also gets rid of noise. Noise is that unwanted spurious signals that we do not want. That's what noise is. It's that that y'all probably heard in the radio the other day. Yes? No? Maybe?
Sir.
Okay, cool.
So it doesn't stop it like a low pass filter, but it just brings it down.
It just brings it down to the level it needs it at and allows things that are lower than a megahertz to pass through.
So once it like brings that two megahertz down to 1 or less, then it will pass it through.
Correct. Absolutely.
Sounds good, sir.
That is absolutely correct. Next we go to this mixer here. This is our local oscillator number 2. It uses something called phase lock looping to tune its oscillators. It is considered what's known as an injection frequency. These frequencies are called injection frequencies. The 140.16 megahertz, that's the injection frequency that gives us our second IF. And I can show you guys that through math. So go ahead and add 140.16 plus 0.240 and tell me what you get. Because some of you were probably wondering, what the heck is this first IF thing and why do I care that it's 240? I typed it out for y'all. What you got, Aaron O'Brien?
Maybe 140.4.
It'd be 140.4. Absolutely it would. Is this not 140.4 right here that we're getting out of the mixer?
It is.
It is. And that is also our second IF. Now we're going to get into what's happening at this local oscillator 1 on our next slide here, so I don't want to jump too far ahead. Now that we have what's known as our second IF, oh, and this, let me explain this for y'all real quick. This is the phase lock looping. In case y'all are wondering what phase lock looping is, this is the inside of these oscillators here. What's happening? This is called a voltage controlled oscillator. They're producing that 140.16 injection frequency right here, and they're sending it back through this PLL to lock it in. It goes back through, and then it comes up and generates it and puts it into this mixer so that you can do that math there and get the 140.4 megahertz. And this is what's happening with our second one as well to get those frequencies. But this one is variable, and we'll explain what's going on there. It's also known as a subtraction mixer. When we go through here, we go to our bandpass filter, much like you guys probably got explained in Dolan Hall. A bandpass filter is like going to a concert and having a backstage pass. That's the term I believe they use for y'all in Dolan. If you have that backstage pass to the concert, you can get through. You can show it to them. You can be like, cool, I want to go meet the band or whatever. If you do not have one, you're probably going to get kicked out. Yes?
Yes, sir.
Perfect. Not speaking from experience, just letting y'all know. Anything that's not 140.4, for example here, is not going to get through. That's what they're trying to tell you with a bandpass filter. That's it. Why do you guys think we have these amps here? That's a good question for y'all.
To bring it up so that when it finally gets to the antenna, it can shoot out.
Perfect. That's what an amplifier does, and you heard me say that before. An amplifier brings that signal level back up. Another reason is we just sent it through an attenuator to drop the signal level down. We dropped it down with a low power filter, low pass filter. We sent it through a mixer. We sent through this oscillator here, so it got mixed up, it got attenuated, it had some loss. It had a lot of signal loss before it even got amplified to get through this bandpass filter. So these amps are here to one, this one is making sure it gets through. Once it goes through this bandpass filter, which is looking for a specific frequency, it's going to need to be amplified again because it's going to go through another attenuator. Now, something to note with these attenuators here, they're part of what's called TGC, not THC, the stuff that's legal in Washington. This is transmit gain control. It holds the power at the antenna constant while variable voice levels are coming in. Now, this is at the antenna. Remember that. On receive side, we're going to talk about it again, the digital attenuators, but they're going to have something called AGC, that's automatic gain control. And that's responsible for holding the power constant while the variable voice levels are coming in at the receiver, the thing you talk into. Because when you receive, you don't have an antenna you listen to, right? We're not trying to transmit RF into our brain, are we? I mean, we do that enough all day with Bluetooth and cell phones. We don't need to do it at work, yes?
Yes, sir.
Perfect. Everyone's like, what? Bluetooth, cell phones? We put RF in our brains? Yeah, you do. Awesome. Let's talk about this math down here, because everybody likes methamphetamine, right? Helps you concentrate. When we're mixing with the second IF output, it's a 140.4 megahertz, and the variable LO, that's a variable local oscillator now. This mixer generates the carrier frequency, 1.6 to 59.999. What do we know about that carrier frequency? What is that the frequency for?
For both HF and VHF.
Not for HF and VHF, it's the frequency for what? What is this device we're using called?
The AMPRC 150.
Yeah, this is the frequency for the AMPRC 150. Now that's a good point you brought up because I want to touch on that. The 1.6 to 29.9999 megahertz range, that's the HF range for the radio. The VHF range, we only touch a small portion of that with this radio, and that's what we use for that FM mode typically. But remember, VHF extends from 30 megahertz to 300 megahertz. We're not capable of doing that full range with this radio. Nor do we need to. This is an HF radio. Here's the example down here for you guys, so you can understand why that math, why does it have to, you're probably wondering why it has to be 140.4, correct? And this is why. Because any of these numbers you subtract between 200.399 to 142 is going to equal the frequency range of the radio, some variation of the frequency that you plug in. If you plug in 30 megahertz into the front of the radio, you're going to have to do the math in here. Well, you won't have to do it. The radio is going to do it for you. But you can see if you plug in 30 megahertz how to get the math done in here, correct?
Yes, sir.
Perfect. Cool. We're not going to ask you guys to do math. Don't worry. You're not going to have to do that. Everyone's probably like,
But I
whew.
like math.
Okay, well, you can go ahead and do math. That's fine. It's only going to help you. Now, when we come out of this second mixer, we now have our carrier frequency. It is no longer an IF. Remember that. This is the only IFs we have in the radio. This is your second IF in transmit, 140.4 megahertz. Your first IF in transmit was what? What was the first IF in transmit?
140.16.
Negative. That's an injection frequency.
$140.4.
Negative. That's your second IF.
240
240 what?
kilohertz.
240 kilohertz. Very good. The first IF in transmit was 240 kilohertz. Remember how you got to this 140.4, your second IF? That's how you got to it. You had to add 140.16 plus 240 kilohertz. Very good. Let's talk about this path real quick before we move on. If you do not have what's known as an external power amplifier hooked up, or that base station configuration that you all saw in the back of the room, did you guys see that?
Yes, sir.
Nice. If you have that hooked up, you guys will go through what's known as the exciter bypass down here, and you will literally do exactly what it says. You're going to bypass all of these things because you won't need them. But if you do not have it hooked up like you guys did, you'll be going through this top portion here, and it's going to have 100 milliwatt output. If we do go through the bottom portion and you have the external PA hooked on, we're going to reduce the signal by 23 dB. The reason we're doing that is because that power amp is capable of doing up to an additional 250 amps, or 250 watts of power. That's going to boost your signal strength back up. That's what power does. It pushes more signal strength, or more signal through, more gain. One thing to note when we come to this next section here, we go to the final PA, you do not need to use that portion of the radio. It doesn't go through this again if you have that external PA hooked up, that external power amp. Now, if you do have it hooked up, or if you do not have it hooked up, it's going to use this. And then we're going to go through what's known as the post-selector filter section of the radio. Why do you think it's called the post-selector filter section?
Because it's after all the selection.
It's after everything else that happened in the radio. It's happening at the very end. Very good. It's that epilogue. So the signal is routed through various filters that attenuate harmonics. The filter is determined by a frequency or modulation using table 3-2 in the intermediate maintenance panel, which I want you guys to go to right now because I'm going to ask you a question. So everybody go to 3-2 in your intermediate maintenance manual. And I would like to know, if I was using a frequency of 22 megahertz, what HF filter band would I be using, 1 through 8? Which one would I be using?
You said 3.2.
3-2.
What was the frequency you were saying again?
20 megahertz. A 20 megahertz frequency.
That would be band 6.
Correct. I think I actually said 22, but yeah, either way, it would have been that. It would have been band 6. Absolutely. And everybody sees that here on 3-2? That's band 6. That's what he said.
Yes, sir.
This is what band 6 looks like. Blown up right here. There's band 6. Remember, this is what's known as a simplified block diagram. That's what this is right here. This is a more blown up version of what's going on in A3, A2. This is a unsimplified or functional block diagram. It shows you what everything is inside of there. So let's go back here. One thing you guys want to note is this BCI filter on the bottom, it's for AME. Does anybody remember what AME mode is?
It's like that alternate mode.
Not an alternate mode. It's one of the modes that the radio has. What would we use AME mode for?
I know AME had to do with the single sideband, I believe.
We would use AME mode to talk to AM radios, to talk to citizen band or other AM radios that did not have the capability to talk to single sideband. So what it does is, in AME mode, it reinserts a little bit of the carrier back into there for the upper sideband, because it has to be done on the upper sideband. The lower sideband portion of this is called something else. But for BCI, this is going to use the AME, and what it does is, like I was saying, it puts a little bit of that carrier back in there, inserts it back in the line, and then you can talk to those AM radios out there, those citizen band radios. Pretty cool. Remember, we are always going to use 2 of 9 filters, and when you look at this, logically it makes sense. When we come through here, we're going to use one of these 2 filters. We're going to use either a band 1 or the AM BCI filter, and then we're going to come down here, and we're going to use one of these 8 filters that we have left. And there are 9 filters because this counts as a filter. Make sense?
Yes, sir.
Okay, cool. Y'all are very talkative this morning. You're killing me. Okay, we're going to go to our directional coupler next because the high-level limiter does exactly what it says it does. It limits high levels from getting through the radio, as in our VISWAR, which is your voltage standing wave ratio. Our directional coupler's job is it takes that VISWAR data, it produces it, and it helps tune the antenna coupler. So it's going to pass that VISWAR data that it's collecting from the radio onto the antenna coupler so the antenna coupler knows how much impedance is coming through and how to match that impedance as it comes through. So it actually gets through the radio and transmits. We do not want an impedance mismatch because that would cause voltage to come back through the radio and cause a bad VISWAR ratio. So basically like a 3-to-1 is a bad VISWAR ratio. That's not something we want. This high level limiter, if that does happen, it'll actually shut the radio down. So none of these sensitive things behind here break because filters are very sensitive and they'll pop when wrong voltages or wrong frequencies come through them. They'll just pop and you'll get some magic electronical smoke that we all call it that. You guys will hear it like called like blue smoke sometimes. It smells terrible.
So all this does is it basically just sends it to the next spot and tells it an impedance.
The directional coupler, yes, it produces the VISWAR data, the voltage standing wave ratio data. This is where it's produced in the directional coupler. And it'll also use that information and pass it to these filters so that these filters, this PA here, it'll use this bias control thing so this PA knows what to send, how much amplification to send through the filters for the specific signal you're sending, for the specific range, right? So for the range of the radio. Does that make sense, what I just said?
I'm still a little confused, I guess.
What are you confused about?
Well, I'm just trying to put it in a way that makes it really simple so I understand it better.
Okay, so the simple way to remember this is the directional coupler produces VISWAR data. That's what it does.
Produces what, sir?
VISWAR data. This part right here. That's what it does. Then it passes that information on to the antenna coupler here, which does this. It does impedance matching, and the coupler control tune data is used to switch the various inductor and capacitor elements into and out of the circuit until a good impedance match is found. So it's going to bounce that signal back and forth basically until it gets what it wants right here. This is what's happening in the antenna coupler. It's going to bounce between these inductors and these capacitors right here. These other inductors down here until it gets exactly what it wants to send out through the antenna here. Make sense?
Yeah, making more better sense.
Mo beta? I love that. That's fantastic. Mo beta. It's one of my favorite things to say. Awesome. And that pretty much covers all of transmit for y'all so far. The impedance matching takes place between the radio and the antenna. That's what the A3, A5 is, the antenna coupler there. It's fed to the J7 antenna connector. It compensates by switching capacitors and inductors like I showed you right here. Boom. And then there are a couple of different types of antennas we can use. One of the ones they always like to list is the OE505 whip antenna. There are, like it says, any number of other antennas that you can choose to meet your mission. For example, a NIVIS, a near vertical incident skywave antenna. That's a type of antenna. It's not a specific antenna like the OE505 is a whip antenna. It describes the pattern in which the antenna radiates. And you guys are going to learn more about antennas and radiation patterns and stuff in block 4. So what is transmit gain control? That's my first question here. We're going to answer these questions. Somebody tell me what transmit gain control is. I will just pick on someone then since y'all aren't speaking up. Aaron O'Brien, what is transmit gain control?
I mean, I can't like exactly pinpoint exactly what it is, but
What does your
I'm
TO say it is? Because remember, I don't need you to memorize this.
Let me look.
Everybody should be looking it up too, not just Airman O'Brien, because it sounds like y'all don't know. I understand that this section is a lot, guys, and that this is kind of where people start to get quiet in this block because they realize that we go very in depth into electronics. And I'm telling you right now, and this is a warning for you all, or a caution, depending on how you want to take it, this is only going to get more difficult from this point on. So asking questions now and trying to understand this stuff is a good thing, because when you get to block 3, you're going to have much more in-depth circuits and diagrams, and even in block 7 later, you're going to have circuits and diagrams that are pretty in-depth. And we're just going to kind of expect you to know it. So ask your questions now if you have them, please. Not trying to scare anybody off.
So the whole time from the digital, when it goes down to digital modulation,
Mm-hmm.
the 240 kilohertz, and it changes back to analog, it stays analog all the way through, and then when does it change to the RF?
It changed to RF here, where I just went back to, because it seems like y'all are struggling a little bit with this TGC portion up here. You see the carrier frequency right there? That's when it's RF now.
Okay.
Okay, so whoever I asked to look up TGC, this is it again for you, I'll tell you again. It holds the power at the antenna constant while variable voice levels are coming in. I understand what I'm going through is a lot for y'all though, and I really do need you to pay attention, but if you do have questions, like Aaron Macheski just said, just speak up and ask your question, guys. This is not intended to make anybody feel dumb or anything. It's just to get you guys the information and get you where you need to be. Nobody inherently comes in knowing all this stuff. We all have to learn at some point. All right, so why is voice converted to digital or data? This is something I spoke about in the very beginning of today's lecture.
It's easier to work with than
Yeah, perfect. It's easier to modulate. It's easier to work with. That's a great answer. I'm great with that. Where is the second IF located? What subassembly?
Would that be the A3 upper chassis assembly?
It's in the A3 upper chassis assembly, but remember, what was the question I just asked you? What subassembly is it located in?
A3-1 or A3A1?
Let's see if you're correct. Boom, there it is. A3A1. Outstanding. Very good. I'm not going to ask you guys this question because it'll take forever, but do know that question. That is literally what section 3.3.1.1 goes through, and if you guys are following along your TO like I asked you to, this will make sense. Where does digital modulation take place?
Would that be the A2A1 submodule?
Perfect. The A2A1 submodule. Very good. That is where digital modulation takes place. Very good. That was outstanding. I'm impressed. Any questions so far on clear voice transmit before we move on here? Does anybody need a quick break? It's been about an hour since we started instructing. Do y'all
like
do
2
y'all want
minutes
like
to
a quick
anything.
like 5-minute break?
Yeah,
That sounds good.
All right, perfect. Let's meet back up here in 5 minutes. All right, so before we went on break, we talked about the transmit signal flow. We're now doing our interim summary and talking about A1 to A2, A4, our analog to digitized audio here. The A2A1, as we said, does the digital modulation. It does the digital to analog conversion. The A3A1, it contains our analog RF sections of the radio as the IF to final RF. That is where our second IF frequency is located of 140.4 megahertz as well. And then we have the A3A2, which is our final PA, our final power amplification, which we really only use if we have an external PA connected. We then go to the post selector filtering. That's our filtering that happens at the end, hence post. And then we get our VisWare data there, which is then passed on to the A3, A5 antenna coupler and used for impedance matching. That it uses to switch between those various inductors and capacitors in order to get the correct electrical signal sent out and the RF sent to our distant end. We're going to talk about data next. And if you guys notice, there's a lot less red lines coming through here, and this is going to be a much quicker section. And these next couple slides, they're going to kind of go a lot faster because you guys already have the basics down now. When we talk about J3, we talk about it coming in as digital. It's data. So it goes to the DTE, the data terminal equipment, goes to the PTFPGA next. We call that the what?
Traffic cop.
That's the traffic cop. You didn't know he was a cop. I'm not going to say the rest of that quote. And then we go to the CFPGA next. And then we go to the modem. That's the modem that modulates and demodulates now, because notice that even though it is plain text data, it does have to go through the modem because it is data. It has to be modulated. And then it goes to the CDSP, the control data signal processor, and it just does the exact same things it did for the rest of the radio. Any questions on clear data? That is it for clear data. That's what it does. If you guys are following along in your intermediate maintenance value, you would know that this is where we are now. We're on 3.2.2 and 3.3.2.4. That's the transmit clear voice signal flow in CC/CT mode. And then paragraph 3.3.1.6 and 3.3.2.4. That's the transmit clear data signal flow in CC/CT. And real quick, you guys remind me what the difference is between CC and CT?
The CT is only for us, and CC it can be used for the allies.
Very good. NATO and allies. Very good. CT we keep for ourselves. CC is shared. If it's J1 audio, it'll come in just like it did before, as analog, get converted to digital, get adjusted, get enhanced and cleaned up in our VDP, go to the PDFPGA, plain text field programmable gate array, or our traffic cop, and then it's going to get sent to CT, ciphertext, get pushed through the A2, A5 embedded crypto assembly, which is not part of our A2, A4 info PWV assembly down here. That's where CC will stay. And then it'll go to the CTFPGA, the ciphertext field programmable gate array, because it has to come back down through and get processed. And then it's going to be known as a black signal from this point on and not a red signal. If it was red, it would stay down here on the bottom. I'm trying to highlight right here. It would stay here. And that would mean that it's unencrypted. However, it's black now. Notice that. And it is encrypted from this point on because it has gone through our embedded crypto assembly and been processed. It is going to have to go through the BIOP, the black input-output processor, which again controls system status functions for the KDU and the radio. And then it goes through the modem, it gets digitally modulated, and it goes through the CDSP. So not really many differences if it's ciphertext or Citadel cover here, if you guys notice, other than the fact that CC stays inside of A2, A4, and CT comes out and goes through its own embedded crypto assembly. Any questions? Now this red/black thing, you guys are going to hear this differently at every single base you go to, and that's just a fact. You're going to hear red may be black, black may be red, something like that. You're not going to hear it differently. That's just how it works. Will y'all excuse me for 1 second? I'm getting a call from Sergeant Gaston.
Yes, sir.
Yes, Sergeant Gaston.
Yes, sir.
All right, let me unpause here. Okay. Before we took a break there, I was telling you guys all about black and red differences. Make sure you pay attention when you go to your units, though. The local guidance from your ComSec office is going to be different. As I was mentioning, black may be red, red may be black. When we talk about SIPRnet cabling specifically, it's going to be colored red. In some other countries, I've heard that green is used for SIPRnet cables. So just pay attention to whatever base you're at, what their local guidance is. You don't want to confuse those things. But any questions on encryption? If there are no questions, we're going to move on to receive. So we'll go to paragraph 3.3.1.2, This is your second page in your guys' circuits and diagrams that you were handed out if you're following along with those. You can go to your receive clear voice signal flow there in your intermediate maintenance manual. Because we're kind of on some crunch time here, I'm going to just tell you guys what the differences are here. For starters, we have a notch filter right here. That's a 140 megahertz notch filter. The job of a notch filter is to amplify weak signal performance coming through and boost it back up. It's not an amp, but it acts like one, so it's going to push our signal back up to that 140 megahertz range so that we can process it down here in our analog RF section when we come back through. Another main difference, we start with the antenna. You guys can see that?
Yes, sir.
Perfect. One of the other huge differences, the whole thing's reversed. And that's really our big main differences there. The top and bottom modules are swapped, the handset and antenna are swapped, each module's components are reversed, and it has a notch filter. Now let me ask you guys a pretty simple question. The antenna coupler, when we came through on our transmit side, what did it do?
It was impedance matching for.
It did impedance matching. Do you think it's going to change its job on receive?
Nope.
Nope, it is not. Our directional coupler, what did that do? Bueller.
It's a directional coupler.
Yeah, what did the directional coupler do? It passed what to the antenna coupler? What kind of data?
VSWR.
The VSWR data, the voltage standing wave ratio data. Do you think that's going to change its job on receive?
No, sir.
No, it's not. It's not going to change its job. Okay? Nothing is going to change its job when we come back through on the receive side. We just added a couple small things, and there's some things that are reversed, and that's what we're going to go through in these next couple slides here. So the high level limiter, still going to live at high levels. Our filter bands, they're not going to change. We're going to use how many out of 9?
2 out of 9.
We're going to use 2 out of 9. Outstanding. And then we go to our notch filter, which, like I said, is the signal is then routed to a notch filter for improving weak signal performance. Note that these are called the pre-selector filters now. Why? What is a prologue used for in a book?
It's after.
Prologue.
So what's happening before?
Before. It's what's happening before, not epilogue. Yeah. Prologue. Prologue is before. Okay.
Oh, I thought you were asking what they did on the transmit.
No, that's okay. You're okay. All right, so once we're done with that section, we come back down here after our notch filter. And here's where one of the big major differences is with receive that we're going to notice, first of all, is the first mixer of LO1 produces the first IF of 140.4 megahertz. So what are we saying our first IF is in receive?
140.
140.4. Very good. It is then amplified before being attenuated by a digital attenuator. And this is part of the AGC, which if you guys remember, I told you was different than TGC. How? How is it different? What is it holding those varying levels constant at? What do you listen on the receive side? You don't listen on the antenna.
Listen on the mic.
You listen on the handset or the mic. Yes. Yeah, you're listening on the handset or the mic. Very good. So it's then mixed with the 140.16 megahertz local oscillator 2 to generate a second IF of 240 kilohertz. Now, what is our second IF in receive?
240 kilohertz.
Great. What was our second IF in transmit?
140.4.
Outstanding. Outstanding. Make sure you guys know the difference between those, and make sure you sit and read the questions so that you know if it's asking you about receive or transmit when you guys are reading questions. Okay? The biggest thing that's going to trip y'all up on your exams is not stopping and reading a question. Okay, so the 240 kilohertz is then routed through the low power filter. It is amplified and then filtered through a bandpass filter, which is right here. And there's your second IF right here, 240 kilohertz IF. It's pushed out, comes down here, goes to the digital A/D now. If you guys notice, that's different because it's analog to digital, not digital to analog, because we're basically unconverting everything we did and putting it back to the way it was so that we can understand it or that we can process that data. One of the things you'll notice here is they say red. That means they're talking about unencrypted. If they were not, it would go up here and it would be called black. So the signal enters the A/D analog to digital converter before being demodulated at the digital intermediate frequency application specific integrated circuit, the ASIC, DFIF ASIC, and the output will be intelligence. What is intelligence?
The audio or data that was
Audio or data. Yeah,
in
absolutely. That's it. We call this digital demodulation on the receive side because on transmit, what did we call it? Digital modulation. Absolutely. Outstanding. You guys are getting this. I've got confidence in you. So then we're going to bring this on home. The signal is then converted to the analog audio signal. It is finally sent to the J1 audio connector right here. This is the J1 audio connector. That's if it's audio. What is one thing you guys notice is missing here?
the ALC.
The ALC. What can you do on the receive side if you don't have the ALC? What can you, as an individual who's listening to somebody talking really low, do to adjust their volume? For example, if you couldn't hear me in Discord right now, what can you do?
Adjust volume.
You do what?
Adjust volume.
Adjust the volume. Use your phalanges. Turn the volume button up or down. Okay? That's all you have to do. That's why there's no ALC here. We don't need to adjust something. What does our PTF PGA do here on the receive side?
It's the traffic up.
That's the traffic cop. Yeah, that's the traffic cop. He's going to send it, if it's up here, to analog, to audio, out here. And if it's data, he's going to be like, nah, bro, down here, data. That's it. That's all he's going to do. If it was encrypted, if it was CT, remember it'd have to go through here. Use ciphertext mode. And once it goes through this part, it'll do its decryption process. And it will be considered read after it comes out of here. It'll be unencrypted once it gets through and processed. Same with the CC. It is not unencrypted though, remember, or decrypted until it comes out of the CC or out of the embedded crypto assembly. Make sense?
Yes, sir.
Cool. Any questions? Y'all have any questions on anything we went over?
I mean, it's just the same as transmit with little.
That's why I went quicker.